Robert Brown because he's American Belgian. He's not Belgian American, okay? So otherwise, I always wondered if he's Belgian, shouldn't it be Roux, you know? But no, he's Robert Brown. Some of you know that in September 2008, our machine called the LHC started, and then soon had a big accident. Now, if that accident did not occur, and we performed as good as we did during 2011, then I think he would not be black here. Oh, he would probably still be dead now, but okay. So anyway, such is life. C'est la vie, as they say in Brussels, okay? So in fact, Higgs and Brown knew each other. The picture I showed of Anglais talking with Higgs, people say that they never met before that event. So according to Peter Higgs, Robert Brown says back in 1960, this is part of our story, at the Cornell seminar, famous Victor Weisskopf said, let's read it, particle physicists are so desperate these days that they have to borrow from the new things coming up in many-body theory, like PCS. Perhaps something will come of it. So I think Brown probably was recalling why he went on investigating the subject. So let's move on now to the Goldstone theorem. We've already introduced roughly, well, we didn't too much, but from BCS, we had Nambu, and now comes Goldstone. So in Nambu's 1960 influential paper, Goldstone published a result. It was Goldstone that introduced elementary scalar theory. What's a scalar theory? It's just playing, okay? And the Mexican hat. Actually, when we're drinking Belgian beer, I was working hard trying to look at whether there's any Belgian beer that has a wine bottle-like bottom. I didn't find one. Otherwise, I would have brought it here, okay? So anyway, Peter Higgs prefers to call this a wine bottle potential. And I agree with him. I like it better too, okay? So this is the Mexican hat, or wine bottle potential. If you look at it, because of this minus sign, and a positive definite, which this is running out, this lambda here. So actually, this is not a very good view. The zero is here, as defined like this. But this is more negative. So there's a tendency to drop down, away from phi equals to 0. And that's called the symmetry breaking, okay? So this circle here is the phi field having a value of v, okay? So one can go into the mathematics, but this is not a math talk. So let's go on with this. So in this phase direction, as we said already once, that there's no resistance when you push a particle around, and therefore it's a zero mass mode. This is the number goes on both sides. When this thing rolls down and sits here, this here is the imaginary axis. Suppose you sit on the real axis and the fixed value, then you no longer have that rotational symmetry. It's spontaneously broken. So small oscillations around that is massless. Okay, if you didn't pick that up, you believe a theorem. Goldstone theorem. In Lorentz invariant theory, spontaneous symmetry breaking, this kind of effect necessitates massless particles with respect to the symmetry that is broken. Okay, I have some planted statements here. The paper is published as Goldstone, Salam, and Weinberg. Here I put Salam and Weinberg in red because they received the Nobel Prize, not because of this work. And I put Goldstone in black and underline it. He's not dead, okay? But I want to have a comment by Higgs. So I refer to Higgs for the blank, okay? All the time I thought Goldstone was a contender. He still may be, okay? But I heard it directly from Peter Higgs, and I think Professor Kahl must know about this, that for this paper is viewed, here there's an earlier paper. This paper is viewed as the more solid Goldstone's theorem. But Peter Higgs says, at the last minute, Goldstone put his name on it. Sorry, Goldstone, I think this means you're not going to get the Nobel Prize this time round, okay? So why do I call it the terror of the Goldstone theorem? The problem is spontaneous symmetry breaking means you break the symmetry spontaneously through this kind of potential, but it implies massless particles. But what are massless particles? Well, photon is a massless particle. Coulomb force satisfies Gauss' theorem. You know, the force goes has influence at infinite distances. We don't feel that. We have photon and gravity. That's it, okay? So it causes a problem. So what we're going to discuss now is resting on the terror of the Goldstone theorem, proven by sharp theorists. Looks like foolproof, no way to get around it. But at an older stage, Julian Schwinger wrote this influential paper, published in Science 62, questioning, whether this thing can be bypassed. Now, interestingly, Philip Anderson, right? Now, if you look at the title, it's just gauge invariance and mass, and it puts on plasma. So he really got inspired by Schwinger, and people can tell me stories of how Phil Anderson got interested in this. Because when I'm talking about bridging the gap between particle physics and condensed matter physics, here is the reverse. Phil Anderson looking at particle people speak and trying to do something. Now, I won't read the words here, but you see Young Mills. By golly, Phil Anderson talking about Young Mills. That's pretty powerful, okay?
May I just add, because Anderson was an expert in business theory, he knew all this. You ask why he was interested in this.
Mass generation, yes, but Young Mills.
He learned that from Prof.
Okay.
Prof visited Bell Lab often, and Anderson recalled that he learned much of his particle physics.
Okay, so they interacted
from Prof.
even better. So this is roughly called the Anderson conjecture, saying that, hey, by golly, guys, you have two problems. One is a zero mass Goldstone boson problem, the previous page, the terror of Goldstone boson. But hey, man, Young Mills from Anderson is a zero mass problem. Maybe you learned it from Brown, but by the way, Brown is a phase transition physicist, so that's still very impressive. Okay. So he said, well, now we have two massless problems. He said in superconductivity from the plasma, you see how it disappears. So maybe this is what happens. The Young-Mills zero mass problem and the Goldstone zero mass problem pairs together, and he uses the word, he actually puts it in parentheses, or in quotation, cancels each other. He didn't know how to put it, okay?
All this paper was written before TURF, right?
Huh?
All this paper was written before TURF, dealing with the renormalization.
Which paper?
Yes, as well.
Because,
This is 1860s.
yeah, all
This?
this
Oh, yeah,
paper
sure,
will worry about renormalization effect, right?
This one?
Yeah, all this paper.
These papers, they don't care. Well, renormalization is a problem, but the harder problem is the mass problem. Okay.
Also, renormalization contributes to the mass problem.
Nobody proved renormalization even after the Brown-Anglais-Higgs thing. So that comes later. There'll be a remark on that.
Actually, the statement is very, very strange because how can you have two zeros cancel?
That's why I say he puts in,
Yes.
in quotation marks. He knows canceling is not the proper wording.
Maybe solve each
It's
other.
just, you're saying, yeah, right. You have two problems, put them together, that's it. Okay? That's the, what is it? Marxist thing. Two antis makes a positive, okay? So this is the non-relativistic conjecture. That was his drawback and criticized that way. Now, I made a slide on Young Mills. This page looks a little bit dense now, but it's also familiar. I hope in your electrodynamics course you learned this notation. Then QED electrodynamics is so-called a U1, a billion theory. A billion just means commuting because it's a phase and multiplying by phase, the sequence doesn't matter. SU2, everybody knows angular momentum. It's like SU2, and angular momentum do not commute. So that's what non-billion means. So if you remove the indices, it's just this thing. And miraculously, this very compact notation is so-called gauge invariant. It doesn't depend on SU2 anymore. It can be any non-billion gauge group, so long you keep this covariant derivative. Okay, that sounds too much. I want to only introduce, just like what you know, in QED, a billion case, there's a photon, there's a massive particle because of the gauge invariance. But there's a story I call the Pauli and Yang, and actually this is from C.N. Yang himself. The story is Pauli was visiting the institute at Princeton. That was before publishing this paper, and Yang was giving a seminar. And Pauli almost immediately asked, what about the math? And Yang said, blah, blah, blah. And a few minutes later, what about the math? So he said, well, this is a very difficult problem. We haven't resolved it yet. And Yang quotes, that is not good enough. Ain't it? Okay? Anyway, let me not go further on the story, but it's a very deep problem. We do not see further massless isotopic photons. By the way, isotopic spin is an invention from Heisenberg. Okay, so let's not get into it. So remember the Anderson conjecture? Cancel, quote unquote, cancel Yang-Mills against Goldstone. Oh, the reason I mentioned isotopic spin is that the name from Heisenberg, it follows from when neutron was discovered in 1932. Because the masses were so close, Heisenberg said, oh, maybe there's this, let's call it isospin symmetry. Okay, let's not get further into that. But what I mean is that this Yang-Mills connection had an overtone for 2 decades, referring to the strong interaction. And I think, unfortunately, this wrongly led a lot of people. Then came, sorry, this is history, so I do history work. Then came a spat between Ben Lee and Walter Gilbert. Basically, Klein and Lee says, well, if you look at superconductivity, the BCS theory type, what you have is you have a preferred frame. Now, can this happen in relativity theories? And they publish it in physical review letters, okay? They mention Anderson. This Gilbert paper is only a little bit more than a page. Nowadays we call it a comment on the physical review letters. It is very terse and basically says something you know, but in a very mathematical way. Come on. In relativity theory, there's no preferred frame. So you can forget this. Okay? Now I hope you read this. Walter Gilbert must be, he's still alive, so must be an extremely smart guy, because the same year he rose from assistant professor of physics, look at the address, to associate professor of biophysics. And a few years later he became professor of biochemistry. And a few years later he received a Nobel Prize in chemistry. So he made a smart move. Stabbed someone and then went the other way. Okay. Now we get to the history-making thing. Now look, I just outlined the date thing. In the end, you know that matters. Priority. This first reference is that Schringer paper. We didn't go into it because Schringer is a deep thinker and a great power mathematician, if you want. So again, it's coming, their mindset is about strong interactions. Okay? They give credit to Nambu, as we stated earlier. The problem is the zero mass guy. Can we get around it? Because zero mass being non-observed means you're dead from the start. They go on and say that actually the massless guys, in the setting we're going to discuss, is what happens, it's like what the Anderson conjecture is. You have two massive things that come together and do something miraculous. So very briefly, let me outline what they did. By golly, scalar electrodynamics. You don't need to get into particle physics or particle field theory. But most people learn electrodynamics with scalar electrodynamics. It's very simple because this is the J mu, the motion of charge, okay? And this is called the seagull. So this Lagrangian you can, this Hamiltonian, the interaction Hamiltonian you can look up. In the scalar electrodynamics, to have this non-trivial charge motion, you need a complex scalar field, as written here. So what does spontaneous interbraking mean? Remember that Mexican hat. As I'm waking up from my beer, I'll use Mexican hat now, okay? So if the field has a vacuum expectation value, you plug it in. So this phi 1, oops, this thing has ran out. If you do the very simple math, phi 1 has a constant value. Phi 2 is 0. Now if you take the derivative on a constant value is 0, but for phi 2, you take the derivative, that's this term, okay? So that means around the vacuum point, if you make small oscillations, the interaction Hamiltonian turns like this. Likewise here, it's dominated by the constant value. So that's very simple math, small oscillations around the solution, the vacuum point. But pictorially looks like this. I'll explain this pictorial thing. Well, actually, it's not difficult. This is a direct translation of this. So you have two powers of phi 1 that look, and look at this, there are 4 legs, okay? There are 2 particles, phi times phi, and 2 particles, mu and mu. So you have this thing. Here it's a little bit more complicated, but you notice that this thing is e squared, whereas this thing is e. So at the same order in e, you need 2 e's. So you have 1 power of phi 1 and 1 power of e, and you bring in this phi 2 that propagates over and repeat the whole thing. So these 2 diagrams are at the same order. So then they show that I'm not introducing this, but the so-called 2-point function of the photon field propagation has this kind of a function. But if you put it together, there's one thing that you may remember. What does current conservation mean? When you contract J mu with Q mu, it vanishes. That's a conserved current. Likewise, pi mu nu, this object here, in 4-dimensional notation, when I contract with Q mu, it vanishes. So explicitly, this form, a constant times this product, when I contract with Q mu G mu nu is Q nu. Q mu is cancels the Q squared, so Q nu minus Q nu is 0. So I've shown for you this holds true. How do we see this? Now, this thing is trivial. That's the G mu nu here, and this coefficient. Now I read this diagram. I have E, phi 1, d mu in momentum space is Q mu. So I have a power of E, phi 1, and a power of Q mu. But this zero mass object propagates like 1 over Q squared. If you have done a Fourier transform of 1 over R, it transforms to 1 over Q squared in free vector space. So you know that 1 over Q squared corresponds to the massless photon. So you put these 2 together, you get a gauge invariant result. But what happens? The thing is, if you had only this term, this thing violates gauge invariance. But now, this coefficient is a gauge invariant mass. Okay? So this is how Anglais got his Nobel Prize, so to speak, to show a covariant mass by having this statement here. Oh, I just said this. So I just said that this Q squared is this zero mass object, that's this propagator here. Okay, actually my time is up, but Bob, you control the time. Maybe we stop after we finish the Higgs page, okay? So this, as I said, this is the gauge invariant vector mass. And the paper further explores when you put in indices for Yang nodes and the conclusion is unchanged. So it's a general phenomenon. Oops, what happened here? So this is Peter Higgs. His first paper will tell the story. It's published in Physics Letters, not Physical Review Letters as in the previous one. By golly, it has only 1.1 pages. Just 1.25, 1.05, sorry. Remember the Gilbert thing. So he says roughly something like that in gauge theory, once you know gauge invariance is proven, you are allowed to choose a gauge. And if I choose a gauge fixing, there is kind of a special frame. So it's a freedom within a gauge theory setting. So he said this can, so he published this way. By the way, this paper has more citations than the other one. Okay. So in this paper he says, a 1.1 page paper, he says, we're going to have another note to explain further. So this is the other note. And it was rejected by Physics Letters. Famously rejected. Thank goodness, okay? Basically they said, it's good for nothing. And let me try to analyze it and say, why did Peter Higgs get rejected this time? This paper was sent out on July 20. He's very precise. He remembers the day of the week. July 24th, Friday. Send up. The Physics Letters office is at CERN. So a week later, he sends off a second paper. I imagine that even the editor felt, gosh, this guy's doing, serial publications, and this is not very ethical, right? Why didn't he combine these two together in one single two-page article, right? but the benefit of physics, I think he rewrote it. Well, he didn't rewrite it. He just added more physics motivation and actually published in Physics Review Letters. The strange thing is the three big papers are all published in Physical Review Letters, although maybe not fully deservingly so. Okay, so okay, these are words maybe I skip over. If you read this, compared to his writing, here he does get more physical. Okay. Okay, this looks a little bit longish. Maybe to save the time, I just say he gets two equations. One is a massive vector field, one is a massive scalar boson. And famously, he gave the scalar boson mass. The scalar boson is the other direction, a small oscillation in a non-broken direction. It's a precise statement, although it's not quantized. So you see, to call it a Higgs boson is okay in this sense, that only in this paper this thing appears. The Nobel Committee cites his remarks mentioning the weak interaction and mentioning that the photon remains massless as a kind of a foresight of what happened later. This is the second statement besides the equation and explicit mass. He has this kind of a little bit esoteric statement, incomplete multiplets. Well, remember you have a complex scalar, so it has 2 degrees of freedom. One gets so-called eaten by the Higgs mechanism. One remains. So your 2 degrees of freedom, only one is left. So your 2-degree multiplet becomes only 1 degree of freedom. So he says, as a generic phenomenon, if you have spontaneous symmetry breaking and this mechanism, then you're left with incomplete scalar representation. Okay? So this is the second statement. He didn't say so. Therefore, please name it Higgs boson in the future. He didn't say so. This footnote, he had to add. He mentions later that he learned that the referee was in fact Nambu. But the referee told him that, there's another paper that came in just as your paper arrived, published just as your paper arrived. So he comments on Anglais and Brout, but strangely enough, well, of course, he didn't know that the referee was Nambu. But strangely enough, both Higgs papers did not cite Nambu, although it can be traced back to Nambu's efforts. Okay, this comments. Okay, maybe I finished these footnotes. Some of you may know the famous Polyakov and Migdal. This paper, you read carefully. Well, let's forget about the English version, but the Russian version was published in the middle of 1966. So that seems to be too late. But the story has it that the paper was written in the first half of 1964. And if you check it up, these two guys were not even 19. Okay? Great Russian education system. So, unfortunately, because of this other gap between the Western world and the Soviet world, these two guys didn't get the credit. In this sense, I put this paper ahead of these two. This is not belittling Gurulnik, Hagen, and Kibble, but just saying in this drawing game, timing does matter. People say they had a more comprehensive paper, but it's a little bit mute when they faced more difficulty. Okay?
The Russian paper only addresses strong interaction.
Only what?
The Russian paper
What about it?
only addresses strong interaction, not the weak interaction.
Well, these papers don't explicitly say so, but their mindset is actually a strong track. Only Higgs, that's why the Nobel Committee mentions it. He mentions the weak interaction and the photon. Okay? But whenever people mention Yang mills, predominantly people think about the strong interaction.
Yeah.
That's how it arose. Isotopic
But later it's applied to the weak interaction, not the strong interaction.
Hmm?
But later is the Weber's law.
I'm coming to that, if you allow me.
Okay.
Okay. Following the statement of the chairman, the history that's made is not just the Higgs mechanism, but precisely that the standard model arose out of this. So here I only talk about the actual dynamics and leave out matter fields, because otherwise it's too long. Everybody knows this. SU3 plus SU2 plus U1. So 4 major pieces of work. One is fully experimental, cited here. Weinberg and Salam, as Bob was hinting at, actually Peter Higgs himself acknowledges this. Because they were all, including Brout and Anglais as well, they were all thinking in terms of the strong interaction, the absence of, this isotopic photons. That's what they were bothering. Schringer as well, trying to get masses. But several years later, Weinberg would, pick up his classmates, his high school classmates' note, and married Higgs mechanism together. And Salam did it independently half a year later, and they're in red because they became Nobel laureates. Okay, maybe not. I did not go through this, but there was a remark about renormalizability. Okay. In all this backdrop, besides mass, the renormalizability of non-Gun gauge theories was an extremely difficult problem. Okay, and mass was only part of it. And it took a young person, a graduate student, to finish it. Rings like McDowell and Polyakov, of course, were undergrad students. Okay? Let me not repeat this whole story, but the right-hand side is more transparent. 1979, electric theory. These guys received the Nobel Prize. Experimental discovery of the actual massive bosons, a prize. Renormalization got a prize. Nambu got his prize. And this year we have Anglais and Higgs. So we mentioned the weak interaction at the beginning as part of our common heritage with this page. Rutherford, our common grandfather, Fermi, our older brother sounds too close, but he bridges both worlds. This is the modern picture. this W boson